Alrighty, so tonight we're going to be talking about writing and naming chemical compounds. So there's nothing new in the notes tonight. I'm just revisiting the same information and maybe trying a different way of talking about it so that we can really make sure that you guys understand it for the quiz. And more importantly, for moving on for the rest of the year. So we're going to be writing and naming chemical compounds. And the first thing that we need to do when we're trying to name or write a chemical formula is figure out, are we talking about an ionic or a covalent compound? So ionic compounds are made up of a metal and a non-metal. And so if you had to look at these compounds, we'd first want to decide, is this ionic or covalent? So sodium chloride, ionic. And yes, it is, because sodium, Na, is a metal. It's found on the first group on the periodic table. What about CH4 or carbon tetrahydride? Is that a ionic compound, metal and a non-metal? The answer is no. Both carbon and hydrogen are non-metals. Even though hydrogen is found in group 1, it is kind of one of those floaters and it is technically a non-metal. Calcium chloride would be an ionic compound because calcium is found in group 2. And potassium hydroxide, metal or non-metal, or ionic compound containing a metal and a non-metal? Indeed, yes it does. Potassium is also found in group 1. So that's the first thing. Covalent compounds are made up of only nonmetals. So if we look at CO2, NH3, MgBr2, and C2H6, CO2, are they both nonmetals? Yes, carbon and oxygen are both nonmetals. NH3, yes, they're both nonmetals. Even though, again, hydrogen is found on the left side of the periodic table, it is technically a nonmetal. MgBr2 is not two nonmetals. Magnesium is, in fact, a metal. It's in group 2. And C2H6, both of them, yes, they are nonmetals. Okay, so if there's a metal present at any point, what kind of a compound is it? And I hope in your head you're screaming, ionic! Okay, so if there's a metal, it's ionic. If it's just nonmetals, it's covalent. Alright, so how do the naming conventions differ? What's the difference between ionic and covalent? Covalent compounds, all the nonmetals, are only compounds that utilize the naming convention of prefixes. So they're the only compounds that have prefixes. If it has a prefix, it's covalent. And these prefixes are used to indicate the number of each element present in the compound, because that's the thing about covalent compounds, is that we can have different types of bonding. We can have double, triple, single bonds. So we can have carbon and hydrogen in a molecule, or carbon and oxygen in a molecule, and have different numbers of different carbons and hydrogens based on how many bonds they're sharing between them. So we have to indicate how many of each element present there are in the compound through the utilization of prefixes. Ionic compounds, when they're metals and nonmetals, are named with the metal or the cation first, then the nonmetal or the anion. The number of each element present is determined based on the charge of each ion. Okay, so ionic, you don't have to use prefixes because we know how many of each element is going to be present based on its charge. It has nothing to do with the prefix, and it's all based on charge. Both of these, the second one, either the nonmetal or it's always the nonmetal because covalent is always nonmetals. The second element always ends in "ide", but if it has a prefix, then that's going to be covalent, and if it doesn't, then it's going to be ionic. So, again, if there's a prefix, what kind of compound is this? You should all be screaming covalent. Alright, so let's talk specifically about covalent. So naming utilizes the prefix. When we're talking about covalent, we use prefixes. So CCl4 and N2H2. Our prefixes are as follows: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay, those should be committed to your memory. So if we're going to be naming this, we have to use a prefix for both the first and second element. The only time, and this is the only time we can exclude a prefix, is if the first element has 1. So this does not need to be monocarbon tetrachloride. We can just say carbon tetrachloride. But over here, N2H2 needs to be dinitrogen dihydride, okay? So the only time you can exclude a prefix is if it's the first element and it's mono. If it's the first element and it's di, you have to include it. If it's the second element and it's mono, you have to include it. But if it's the first element and mono, you can exclude it. For chemical formulas, you look at the prefixes and then just put those numbers as subscripts. So phosphorus pentafluoride and dicarbon hexahydride. Phosphorus, there's nothing there, so it's just going to be P. Pentafluoride, it's F, but its penta is 5, so it's going to be PF5. Dicarbon hexahydride, 2 carbons, so C2, and then hexahydride, 6 H's, so C2H6. All right, not too complicated. This is probably your guys' favorite naming because you love prefixes and it's super easy once to write the chemical formula. Okay, but I don't always include just covalent compounds on a test because that would just be way too easy. All right, so let's talk about ionic and finding the charge of an element from the periodic table, because half the battle with naming ionic compounds is figuring out what the charge is, because it's all based on charge. So we can do this from the periodic table. Here's a blank periodic table. I'm going to fill in the first row, okay? Your hydrogen, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and helium. Now, the charge of an element can be found from its location on the periodic table. All those in group 1 under hydrogen have a +1 charge because in order to reach their full valence shell, they need to lose 1 electron. Electrons are negatively charged, so the loss of an electron means you are more positive, so +1. Beryllium is a +2, and everything in group 2 is a +2, because again, in order to reach its full valence shell, it's going to lose 2 electrons, or lose 2 negative charges, making it +2. Boron is going to be +3. Carbon, it's right in the middle. It's just as easy to lose 4 electrons as it is to gain 4 electrons. So carbon and its group 4 elements are going to be ± 4, which tends to mean that these don't actually form ionic compounds. They're more likely to be forming covalent compounds. Nitrogen over here with its 5 valence electrons, it's easier to gain 3 electrons than to lose 5. So it's going to be a -3 because gaining negativity means you gain a negative charge. Oxygen and all the ones underneath it in group 6 are going to be -2. Fluorine, -1, and everything under fluorine in group 7 is -1. And then helium and all the noble gases already have a full valence shell. They do not want to lose or gain electrons, so they're going to have a charge of 0. Now the tricky part comes with our transition metals. The transition metals charges must be given to you in the name, Fe3. So if I'm going to name it to you and you have to write the chemical formula, I have to give it to you in the name, iron 3 or Fe Roman numeral 3, okay? I cannot expect you to guess that. The only way that I'm not going to give it to you and expect you to know it is if you have to determine the metal's charge based on the charge of the anion that's attached to. Okay, so let's look at this. So ionic, when we're naming, it goes the cation, then the anion, and the anion gets an IDE ending or "ide" ending. So for MgCl2,
Go Crane for cell 6002.
sorry guys. So for MgCl2, that would be magnesium, and then chlorine becomes chloride. So magnesium chloride. Na2O, sodium and oxygen, becomes sodium oxide. Okay? It's that simple. It doesn't matter that chlorine is a 2 or sodium's a 2. We don't include prefixes. We just name the cation, then the anion, and the anion gets an "ide" ending. Now for chemical formula, you need to have a balanced or neutral compound, and charges need to stay out of it. So your compound should never have their charges included. So let's take a look. With calcium bromide and aluminum oxide. So calcium bromide, you've got calcium and bromine. Calcium's a 2+ and bromine's a 1-, and I know this based on their position in the periodic table. Now if I add those two charges together, 2+ and a 1-, I get an overall +1 charge. That is not neutral. So I need to do something. If I've got too much positivity, I'm going to need to add more negativity. So I do that by adding another bromine, which has a 1 minus charge. So now I've got 2 plus and 2 1 minuses, so a total negative 2 charge. So my overall charge right now is going to be 0. That's neutral. So I know that I've balanced out my charges. So then the formula for this compound is going to be CaBr2 because I used 1 calcium and 2 bromines. Now, aluminum oxide. Aluminum is a 3 plus, oxygen is a 2 minus. If I add 3 plus and 2 minus, I get an overall charge of positive 1, which means I'm going to need to add some more negativity. I can, again, only add this in terms of oxide, O2 minus or O minus 2, which now means I have a 3 plus and a 4 minus. So now my overall charge is going to be negative 1. So now I have too much negativity, so I'm going to need to add some positivity back. So I'm going to add an aluminum. Now I've got a total of 6 plus and 4 minus, so my overall charge is going to be positive 2. So now I need to add negativity again. So I'm going to add another oxygen. Now I have a total of 6 plus and 3 times 2 minus, which is 6 minus. So now my overall charge is going to be neutral. So when I write the chemical formula, I use 2 aluminums and 3 oxygens. So I'm going to have Al2O3. All right, so that method should work for most people. Now, some people are like, oh, that takes too long, I don't like that, which is fine. You can think of it in another way. If I look at calcium and bromine again, calcium's a 2 plus, bromine's a 1 minus. So the common number there is 2. I only need 1 2 plus to make positive 2, but I need 2 1 minuses to get negative 2 for it to balance out. So that's why I have CaBr2. Over here with the aluminum and oxygen, between 3 and 2, the common number is 6. And so in order to get 6 from 3, I need 2 3 pluses to get 6 plus, and 3 2 minuses to get 6 minus and have it neutral and have it be even. So that's why I have Al2O3. Whichever methodology works for you, I don't care, but I wanted to put them both out there so that you can see where we're going, because some people were having a hard time with common numbers. Okay? Now, polyatomic ions, because these are polyatomic ions, they do ionic bonding, okay? The ion and the ion, it's ionic bonding. So we still have to do very similarly like we just did, we have to balance the charges. So when you're looking at chemical formula, make sure that you know that it's a ClO4. That's not chlorine tetraoxide, but rather perchlorate. I will only ever use those 18 polyatomics I gave you to memorize, but you need to remember that those exist and they have names, and therefore we should use them. So, for example, here we have calcium, and CO3 is carbonate. So this is going to be called calcium carbonate. Oops, sorry. Okay, calcium carbonate. ClO is hypochlorite, and Na is sodium, so that's going to be sodium hypochlorite. Over here we have beryllium and NO3, which is nitrate, so that's going to be beryllium nitrate. Here we have magnesium and acetate, so that's going to be magnesium acetate. Lithium and sulfate, so lithium sulfate. And strontium and permanganate, so strontium permanganate. Notice again, this is ionic bonding. We did not do, I didn't do magnesium diacetate or strontium dipermanganate, because it just, number one, sounds awful, but number two, is not necessary. We're doing ionic bonding here. I don't need prefixes. I only need prefixes for covalent bonding, and this is not that. So keep that in mind. And notice that I had to use 2 lithiums here to balance out the charge of the sulfate. So you still have to keep everything balanced. So we need to balance the charges and make a neutral compound. So magnesium sulfate, magnesium's a 2 plus, sulfate's a 2 minus. So those cancel out, leaving with MgSO4. Potassium and chromate, potassium's a 1 plus, chromate's a 2 minus. So I'm going to need 2 potassiums to balance out my 1 chromate, so K2CrO4. Strontium phosphate, strontium's a 2 plus, phosphate's a 3 minus. This is getting a little bit trickier because now I have to balance between 6. And so strontium, I'm going to need 3, and I'm going to need 2 phosphates. But phosphate, since it's a polyatomic ion and I need multiple of them, I must remember the parentheses around the phosphate. If I don't include that parentheses, it looks like 42 oxygens and 1 phosphorus, which is nothing. Okay, that doesn't exist. So don't forget those parentheses. And then aluminum carbonate, I've got a 3 plus and a 2 minus, so I'm going to need 2 aluminums and 3 carbonates. And again, those don't change the name at all. It's just balancing that charge. Okay, but what about those pesky transition metals? They're still metals, so they do ionic bonding, but we have to figure stuff out with them. So transition metals can have a variety of charges, and thus the charge of the metal must either be given to you as part of the name in the form of a Roman numeral, or it can be determined given the chemical formula based on the charge of the anion. So let's take a look at that. So let's name these. So given the chemical formula, we can determine the names. So here I have nickel, Ni, and SO4, sulfate. Nickel, based on, sorry, I went two clicks too far. So I have Ni and SO4. So nickel's a transition metal, so I don't necessarily know what its charge is, but I know that sulfate is SO4 2 minus. And since I only used one of the nickels to balance out the sulfate, the nickel must have a 2 plus charge to balance out the entirety of the 2 minus charge. So that's why it's going to be nickel 2 plus and SO4 2 minus. Now when I name this, I have to indicate to people that this is nickel with a 2 plus. So I would say that it is nickel 2 sulfate. The 2 indicating that it's a nickel 2 plus, not that I have 2 nickels, because if you notice, I only utilized 1 nickel. This next one, CuCl2, this is copper and chlorine, or chloride. Now I had to use 2 chlorines to balance out and neutralize the copper. Chlorine, we know from the periodic table, has a -1 charge, but I needed to use 2 of them, so my total negative charge is going to be -2, which means that you needed -2 to counterbalance the total positive charge, which would have been then +2. So here, copper is going to have a 2 plus charge, chlorine is going to have a 1 minus charge, so I need to indicate that the copper has a 2 plus charge. So I say copper 2 chloride. Again, the 2 doesn't tell me that there's 2 coppers, nor does it technically tell me that there's 2 chlorines. It just so happens to balance out that way. What the 2 tells me is that the copper is a 2 plus ion of copper. Now with Fe2O3, oxygen is an O2 minus, and I needed 3 of those. So my total negative charge over there is -6. That means that my total positive charge needs to be +6 to balance that out. But I have 2 irons needed to make that +6. So if I take +6 and divide it by 2, I get that the iron, each of them, was a 3 plus. So the iron each had a 3 plus charge to make a total +6 to counterbalance the -6 coming from the 3 O2 minuses. So this would be called iron 3 oxide. And so that's where it's really tricky. The 3 does not mean that there are 3 irons. In fact, there are only 2. And it doesn't technically mean that there's 3 oxygens, although that does happen here. But it doesn't always. So don't forget, those Roman numerals are the charge of the metal. So let's do another set. Chromium permanganate. Okay? So we've got chromium and we've got permanganate. Permanganate is a 1 minus, but I needed 5 of them, so I have a total 5 minus, so that chromium must be a 5 plus. So chromium is going to be a 5 plus, permanganate's a 1 minus, so this is chromium 5 permanganate. Now I've got AgBr, that's silver and bromine. Bromine's a -1. I only needed 1 bromine and 1 silver, so that must mean that the whole positive charge of silver is +1, so silver +1, bromine 1 minus, so then that becomes silver 1 bromide. And then manganese and hypochlorite, I needed 2 hypochlorites. Hypochlorite is just a -1. So there's a total -2 charge, which means the manganese must be a total +2 charge because there's only one of them. So that's going to be manganese 2+ and hypochlorite 1-. So that should be manganese 2 hypochlorite. It's a mouthful, I know. Okay. So again, the Roman numeral is telling you what the charge of the transition metal is, not how many there are. So then how do we write the formula? So we've just named it. Now how do we write the formula? So nickel 2 chromate. So nickel 2 tells me that it's a nickel 2+. Chromate is CrO4 2-. We need these to balance out. 2+ and 2- do balance out, so this is just going to be NiCrO4. Manganese 4 chlorite. The manganese is going to be a 4+ because it's manganese 4. Chlorite is ClO2 with a 1- charge. I'm going to need 4 chlorites to balance out my manganese. So that's going to be MnClO2 parentheses 4. What about copper 1 carbonate? Copper 1 tells me that it's a Cu1+. Carbonate's a CO3 2-. Sorry about that typo there. If I have a 1+ and a 2-, I need to balance those out. So I'm going to need 2 1+s to balance out a 1 2-. So I'm going to get Cu2 CO3. And for iron 3 nitrate, that 3 tells me that it's iron 3+, nitrate's a 1-. So I'm going to need 3 nitrates to balance out my iron. So I have FeNO3 parentheses 3. Okay. All right. So I want you guys to pause this for a second and work on these. Either give the formula if you're given the name, or write the name if you're given the formula. Do all of these, and then unpause it and check your answers. Okay, so silicon dioxide. So silicon is Si. It's dioxide, so that's 2 oxygens. So it's going to be SiO2. Oh, I'm just giving you, I forgot that I just gave you all of these. So it's going to be SiO2. For calcium chloride, calcium's a 2+, chlorine's a 1-. So we're going to need 2 chlorines for every 1 calcium. Nickel 2 chlorite. Nickel's a 2+, chlorite is a 1-. So we're going to need 2 of those chlorites for every 1 nickel. Phosphorus trifluoride. It's phosphorus, so it's 1, so we can ignore it, so P. And then trifluoride, F3, PF3. Now I used 2 coppers to balance out this sulfate. Sulfate's a 2-. So each of the individual coppers must have been a 1+, so copper 1 sulfate. Here, sodium is not a transition metal, so I don't need any Roman numerals. So I'm just going to name it as is. So sodium chlorate. Aluminum, oh, that should be di. So that should be a Cr, not C, sorry. Aluminum here is attached to chromate, or dichromate, which aluminum is also not a transition metal. Many people make that mistake. It's really close to it, but it's not a transition metal. So I'm just going to name it aluminum dichromate. And then C2H6 dicarbon hexahydride, because we've got a covalent compound there. Alrighty guys, so we're going to be working a lot more on this tomorrow. Practicing, and getting ready for the quiz. Alrighty, have a good night guys.